Today's speaker is Alexey Gotsman from the IMDEA Software Institute. Alexey is an expert in distributed systems and formal verification, and today he will talk about the modular framework for designing provably live and efficient Byzantine consensus algorithms. Alexey, the floor is yours.
Hello, I'm going to be talking about making Byzantine consensus live, and this is joint work with Manuel Bravo and Gregory Chokler. Byzantine consensus is a classical problem in distributed computing where several processes need to agree on a single value. And the word Byzantine means that some of these processes may be malicious, at most f out of the total of 3f plus 1. When you use consensus in practice, you usually use its generalization called state machine replication, where processes agree on a sequence of values. These values are commands that change the replicated state stored at these processes. And by far, the most famous application of Byzantine state machine replication is blockchain, which uses it to agree on a sequence of blocks in the ledger. So Byzantine consensus has been studied for ages, but when blockchain came along, people opted for different kinds of block protocols, and that's because classical Byzantine consensus assumes what is now called a permission system, where the set of participants is fixed. In contrast, blockchain consensus, like proof of work, allows anybody to participate in the system, so the system is permissionless. On the flip side, Byzantine consensus provides hard guarantees on decision finality, but such guarantees are hard to get with blockchain consensus. So both approaches can learn from each other, and for this reason, recently there's been a push to use Byzantine consensus in the blockchain context, usually by electing a committee that will finalize decisions by Byzantine consensus. This has motivated a new wave of Byzantine consensus protocols, more appropriate for this setting, but ultimately they all build on a seminal work from 1999 called Practical Byzantine Fault Tolerance, or PBFT, which was the first practical algorithm in this area. When you think about blockchain, you're usually mostly worried about safety, that you don't have double spends or something. But the blockchain also has to be responsive. And when you design protocols for this context, really a lot of complications arise from the need to ensure liveness. And in this talk, I will propose a framework that separates the management of liveness from the management of safety in Byzantine state machine replication, and in this way simplifies protocol design. Okay, so let me explain what the deal is with liveness. It starts with the bad news, which is you cannot have a deterministic consensus protocol that would be both safe and live in an asynchronous network where there is no bound on message delivery time. So this is a really old theorem called FLP, and intuitively it holds because you cannot really tell a crash process from a slow one. Fortunately, there is a good news, which is networks are synchronous most of the time. And so the compromise people often settle for is to provide safety always and liveness only under synchrony. And such behavior is formalized by what's called a partial synchrony model. It was proposed in another old paper called DLS. And it's a mathematical model that approximates the behavior of real networks. In this model, the execution of the system is divided into two periods. First, there is an asynchronous period during which things don't go well. Messages can get delayed or lost, and clocks at processes may get out of sync. That's because in practice, they're also synchronized using messages. And then at some point, there will be a global stabilization time. So this time is unknown to the protocol, but it exists. And after this time, the network will enter a synchronous period. This means that messages between non-faulty processes will be delivered within an unknown time delta. So it's unknown to the protocol, but it exists. And clocks at processes will track real time. And so, of course, we cannot guarantee much during the asynchronous period, but we would like to guarantee liveness during the synchronous period. So that's the challenge. The way liveness is achieved usually in this setting is using leader-driven consensus. The idea here is that processes are kind of like members of parliament. They can vote to accept a value. And there is one process, the leader, who's like a speaker. So he proposes a value to vote on. And if enough processes agree with the leader's proposal, then we've reached a decision. Usually enough in this setting means 2f plus 1 votes out of 3f plus 1, so a supermajority. Real consensus protocols for this setting are more complicated, but for the purpose of this talk, this kind of a simple picture will suffice. Now, the challenge with liveness here comes from the fact that votes may fail. And that can be because either the leader is faulty, so it makes no proposals at all, or because the network is asynchronous, and so the messages sent by the leader get lost. And we can't really tell the difference between these two situations, so to deal with this, we have to be able to change leaders. Usually this is achieved by dividing the execution into a series of views, where each view is associated with a fixed leader. So for example, you can get leaders to rotate round robin. And then the idea here is that eventually GST will occur, so the network will become synchronous. And because we assign leaders round robin to views, we keep hitting correct leaders. So eventually we'll have a view with a correct leader where the network is synchronous. And so then we will be able to make progress. Okay, so I've drawn this pretty picture as though processes change views instantaneously. In reality, what may happen is something like this. Now recall that before GST, clocks may be out of sync and messages may be delayed or lost. So whatever algorithm you use to synchronize views between processes, before GST will not be able to achieve much. So at GST, processes may be in completely different views, and to achieve liveness after GST during the synchronous period, we need to bring all non-faulty processes into the same view. And we need to achieve this despite the fact that malicious processes may try to disrupt this. So this is the problem of view synchronization, and this is one of the challenges that you need to solve to ensure liveness. Now, as I probably convinced you, ensuring liveness in this context is non-trivial, but until recently, we hadn't had a systematic framework for doing this, and even seminal protocols like PBFT lacked liveness proofs. So for example, PBFT actually came with a detailed safety proof, but had only an informal and brief liveness justification. As a consequence, many of the recently proposed blockchain consensus protocols actually have liveness bugs in them. And in general, when you use ad hoc mechanisms to ensure liveness in your protocols, this just complicates their design. So a way to improve this situation is to use a modular approach where your core consensus or state machine replication protocol runs on top of a component called the synchronizer, which tells processes when to switch views. And so solving the problem of view synchronization is actually delegated to this component. This was the approach that was taken in the very first paper, DLS, on consensus under partial synchrony. And it was also an approach that has recently been suggested in more blockchain kind of work like hot stuff. And so the benefit of this is that you can design the synchronizer once and then reuse it across different protocols. So you get more systematic design. And so what we've set out to do is to realize this vision. And for this, we're making several contributions. First, we propose a specification of the synchronizer component that is sufficient to ensure liveness over a range of modern consensus or state machine replication protocols. In particular, we can give the first rigorous proof of liveness for PBFT. We also propose an implementation of the synchronizer for partial synchrony that handles all its adversarial features. That includes unknown delta and GST, and before GST, out of sync clocks and message loss. Now, out of this list, the most interesting point is message loss. You can think that this is a trivial problem because you can just deal with message loss by buffering messages and resending them. But unfortunately, this will require unbounded space and will make your system prone to out-of-memory attacks. In contrast, our synchronizer uses bounded space. It also has a low latency. For this reason, we call it a fast sync. And we can actually derive tight latency bounds on reaching decisions, so proving not just that consensus or state machine replication protocols eventually reach a decision, but quantifying how fast this happens. Okay, before I go into the details of these contributions, let me make just one disambiguation. So far, I've been using the words consensus or state machine replication more or less interchangeably, but actually they're quite different. In particular, on one hand, state machine replication can be implemented trivially from consensus by just calling it repeatedly as a black box to agree on a sequence of decisions. The problem is that this construction is suboptimal in several ways. The easiest one to understand is that you may actually want to reuse the same leader across consensus instances, like in multipaxes, and then you will not be able to use consensus purely as a black box. And this is actually the approach that is taken in PBFT. So for this reason, we actually proposed two synchronizer flavors. First, we proposed synchronizers appropriate for consensus. That was a paper in Disc 20. And then we generalized it to the case of state machine replication. And that's a paper that's now available on arXiv. So the case of SMR is strictly more general. You can get consensus as a special case. And in the rest of the talk, this is what I'm going to be focusing on. So in the rest of the talk, I'll first present our synchronizer specification, then its implementation, and then finally, I will give you a bit of a flavor of how we apply the synchronizer specification to prove liveness of PBFT. Okay, so let me start with the synchronizer specification. And I will first present the Synchronizer API, which we actually borrow from a recent paper by Naor and Kedar. As I said before, the job of the synchronizer is to tell processes when to switch views. And the synchronizer will do this using a new view up call at processes, asking them to enter a given view V. Now there is a subtlety. The synchronizer doesn't itself know when it should switch views because the rules for this are protocol specific. For example, a state machine replication protocol may want to switch views if the current leader is suspected to be faulty based on some timeouts. And so for this reason, the synchronizer allows processes to use an advanced down call that suggests it to switch views. Now, the next question is what kind of guarantees this API should provide. And the guarantees are somewhat subtle because remember that we have to deal with this messy situation where at GST processes may be in completely different views. And now we have to bring them all together despite possible disruption by faulty processes. And so the guarantees are defined by three properties, which I'm going to present now. The first property is called validity. It guarantees that a process can enter a view v plus 1 only if some correct process has called advance in the previous view v. The important word here is correct, so calls to advance by faulty processes don't count. This ensures that, for example, if all correct processes enter the same view v and they're all happy there and nobody calls advance, then the system will stay in this view forever and faulty processes will not be able to disrupt it. So that's good, but sometimes we do need to switch views. For example, if the SMR protocol suspects the leader of V to be faulty. And so the next property called progress gives conditions under which this will happen. I will present it only in a simplified form. It says that some correct process will enter a view V plus 1 if at least F plus 1 correct processes call advance in the previous view V. So let's take the example on the slide. Here we have 4 processes. That means F equals 1. This means that if at least 2 correct processes, for example, 1 and 3, call advance, then we're guaranteed that some process, for example, process 3, will enter the next UV plus 1. And so what progress allows you to do is to iterate through views in search for one that has a correct leader. There is a bit of a subtlety here, which is progress assumes or requires that at least F plus 1 processes call advance in V. Whereas according to the validity property that I've just presented, even a single advance call can potentially lead to a view switch. So this discrepancy is due to the fact that in synchronizer implementations, we have to be extra conservative to guard against disruption by faulty processes. And so for this reason, as I'm going to explain later, decisions on view switches are taken by supermajorities of 2F plus 1 processes, like decisions in consensus. And 2F plus 1 processes contains at least F plus 1 correct processes, hence the requirement in progress. Okay, now progress guarantees that some process will enter the next UV plus 1, but that's not enough to achieve liveness. For this, we need all correct processes to enter the same view. And now the next and last property ensures that this happens. It's called bounded entry. It guarantees that if a correct process enters a view V, then all other correct processes will also enter the same view V within an interval bounded by a constant D. So D is a parameter of the specification. It's different for different synchronizer implementations. For example, for the implementation I'll present to you later, it's 2 delta. Now, this guarantee is not given unconditionally. There are a couple of requirements here. First, we don't guarantee bounded entry for all views V, but only starting from some view calligraphic V that is existentially quantified. That's because before GST, the synchronizer cannot guarantee much because it can't exchange messages needed to bring all processes into the same view. And so we only guarantee bounded entry for views entered after GST. Then there is the other requirement. It says that no correct process attempts to advance to a higher view within D. Let me explain this in a bit more detail. Imagine process 1 enters view V. And now we'd like to happen that all correct processes enter the same view V within this interval D. But now imagine that process 1 is impatient, and before the interval D ends, it calls advance, so thereby asking to switch to the next view V plus 1. In synchronizer implementations, this may lead another process, say process 3, to enter V plus 1 directly and skip view V. And so for this reason, we require that no correct process attempts to advance to a higher view within this interval D. Okay, so these are the properties. To summarize, progress allows iterating over views in search for a correct leader. Bounded entry ensures that all correct processes enter the same view, and validity ensures that correct processes can stay in the good view for as long as they're happy with it. And so I will shortly explain to you how these properties are used to prove liveness of state machine replication protocols, but first let me tell you how they're implemented. So let me present our FastSync synchronizer. And the key challenge the synchronizer has to deal with is that we have to consider these kinds of situations where processes are completely out of sync, and furthermore, faulty processes may try to disrupt the process of view synchronization. And for this reason, the synchronizer can't just enter a new view once somebody calls advance. Before entering a view, processes will have to communicate. The way this is done is as follows. When a process calls advance in a view V, it doesn't enter a new view straight away. It first broadcasts a special wish message saying that it wants to enter the next view V plus 1. The process will actually enter the new view V plus 1 when enough processes express a similar wish. I'll shortly explain what similar means in this context, but for example, this could be identical wishes. And as usual, enough means a supermajority, 2F plus 1 out of 3F plus 1 processes. And this is to guard against the disruption by faulty processes. Now, to enter a view, we need to accumulate enough wishes, but if implemented naively, this would require unbounded space. So to deal with this, we'll summarize all the wishes we've received into an array where we maintain the highest entry, highest wish received from each process. And now the rule for entering a view is as follows. If you receive 2F plus 1 wishes for views that are higher than yours, then you will enter the minimal view in them. So this is what similar means in this context. For example, if we take the array shown on the slide, I can sort its entries in an increasing order. And now I have 3 entries that are 20 or above. So 3 here means 2F plus 1, a supermajority, and that means I can actually enter view 20. One important point here is that you may be forced to enter a new view according to this rule, even if you haven't actually called advance. And that's important because it allows lagging processes that are in stale views to catch up with the rest of the system. This is not the whole implementation. There is another rule here. So it's as follows. If you receive 2F plus 1 wishes greater than the view you're trying to enter, then you will switch to trying to enter the minimal view in these wishes, and you will relay the corresponding wish. So the rationale here is that among F plus 1 processes, at least one must be correct, so it isn't lying. And so it's of no use trying to enter the view you're trying to enter, because at least one correct process already wants to enter a higher view. And so in this case, you go with this process. For example, if we take the array shown on the slide, and again, sort its entries in increasing order, then here we have 2 entries that are 20 or above. So that's F plus 1. And that means it doesn't make sense to enter view 10. You should enter at least view 20, because at least one other correct process is already trying to enter this view. And finally, there is one last wrinkle. So recall that before GST, messages can get lost. And for this reason, to make sure that our wishes actually get through, each process periodically resends the last wish that it sent. And you only need to care about last wish, which is nice because that means it can be implemented in bounded space. And that's it. These are the two rules of the synchronizer. One acts on 2f+1 wishes. In this case, you enter the minimal view in these wishes. The other one acts on f+1 wishes. And in this case, you relay the minimal wish in them. Some people may get a déjà vu here because these rules are very similar to something called Bracha's algorithm for reliable Byzantine broadcast. It has essentially the same rules, but they act only on sets of identical messages. And that means that Bracha broadcast cannot be implemented in bounded space because it has to keep accumulating wish messages in case one of them forms a large enough matching set. And so really what we're doing here is we're specializing Bracha broadcast to exploit the particular semantics of wish messages by acting on mismatching wishes or by storing only the highest wish per process. And this is what allows us to run in bounded space. Now let me illustrate how this synchronizer operates using a couple of examples. The examples I'm going to show, they consist of two parts. First, there is a scenario that leads the system into a problematic state, and then I show how our synchronizer recovers from it. I'm going to consider a system of 7 processes with 2 faulty processes, 4 and 5, so f equals 2. And then the remaining correct processes are split into 2 groups. First, we have a group of f+1 processes. These are processes 1, 2, 3. And then we have a group of F processes, 6 and 7. Now, initially, everybody is in view 1, and now imagine that they want to advance to view 2. So they send wish for view 2. Now, we're before GST, so some messages may get lost. Let's assume that there is a network partitioning between processes 1 to 3 and 6 and 7. So all the messages going across this partition get lost. Now, at the moment, processes 1 to 3 don't have enough support to enter view 2, because for this we need 5 wishes, so that's 2f+1. But what may happen is the faulty processes 4 and 5 may provide the missing wishes for view 2 just to processes 1 to 3 and withhold them from processes 6 and 7. So this will allow processes 1 to 3 to actually enter view 2, and processes 6 and 7, they will get stuck in view 1 because they don't have enough matching wishes to enter view 2. Now, imagine that processes 1, 2, 3, they're lonely in view 2, and so they try to advance again and send a wish for view 3. Now, the same scenario as before may happen. The faulty processes may provide the matching wishes for view 3, and this will allow processes 1 to 3 to enter view 3. And so this can go on for a while until, in the end, processes 1 to 3 will be in view 9, and they will want to enter view 10. And now imagine that GST occurs, so messages start to get through. So at the moment, we don't have 5 wishes for view 10, so nobody can enter this view. But at the same time, we have to ensure that at least one process enters view 10 that's required by progress, because we've had at least f+1 advance calls from view 9 to view 10. And we also ideally like to ensure that all correct processes enter view 10, because that's what's required by bounded entry. So our synchronizer will ensure these properties using this relay clause that acts on f+1 wishes. So processes 6 and 7, they will notice that there are f+1 wishes for view 10, and they will give up on trying to enter view 2 and instead try to enter view 10 and send the corresponding wish. And so now we have 5 wishes for view 10, and the rule is that we enter for 2f+1 wishes. And so now all the correct processes will be actually able to enter view 10. And so we've got what we wanted. So far, I've only used sets of matching wishes, so I haven't demonstrated the full power of the rules of our synchronizer. So let me tweak this example a bit to illustrate this. Let's rewind a bit to the point we had at GST, where processes 1 to 3 were in view 9 and wanted to enter view 10. And processes 6 and 7 were stuck in view 1 and they wanted to enter view 2. And there was a partitioning between these two groups of processes. Now, imagine we are still before GST, and now the group of processes 1 to 3, itself gets partitioned into two subgroups. Processes 1 and 2 are on one side, and process 3 is on the other. And what we have is that processes 1 and 2, they don't receive any messages sent by process 3, but process 3 does receive messages sent by processes 1 and 2. This can happen before GST. Now, what may happen is the faulty processes 4 and 5 may provide the wishes for the view 10 just to process 3. And so now process 3 will accumulate 5 wishes for view 10, 2 wishes from the faulty processes and 2 wishes from correct processes 1 and 2. And this will allow this process to enter view 10. And then after a while, this process may get unhappy and say, oh, this view doesn't work, so let me call it once again. And then it will start trying to enter view 11 and send the corresponding wish. And so now the GST occurs, and this is the problematic situation we have to deal with. Here, we don't have even a f+1 completely matching wishes. But on the other hand, we have 3 wishes that are 10 or above. And according to the rules of our synchronizer, it allows us to relay the minimal wish out of any f+1 wishes. And so what will happen is processes 6 and 7, they will notice that there are 3 wishes with 10 or above, and then they will say, okay, so let's try to at least enter the minimum in these wishes. And so they will switch to trying to enter view 10 and send the corresponding wish. And so now we'll have 4 wishes for view 10 and 1 wish for view 11. Now, again, we don't have any completely matching 2f+1 wishes, so that's 5, that would allow us to enter a view if we required just matching wishes, but our synchronizer doesn't require exactly matching wishes. We can always enter the minimal view in any 2f+1 wishes. And so here we have 2f+1 wishes for 10 or 11. And so that means that everybody can actually enter view 10. And so now everybody is in this view. And now if after a while, all the other correct processes think that they're unhappy in view 10 and they are call advanced, then the synchronizer will send wish 11. We'll have 5 wishes for the view 11. And so everybody will converge on view 11. And so we'll get into a nice situation. Okay, so this is how our synchronizer works. Now I try to illustrate by example why it satisfies the specification that I presented to you before, but we actually proved correctness of the synchronizer formally. The proof is kind of complicated, but the good news is that it has to be done only once. And then after this, view synchronization mechanics can be hidden under the specification of the synchronizer that I presented to you before. And that means that it can be reused to prove liveness of different protocols. And in the remaining bit of the talk, let me illustrate how we actually use the specification of the synchronizer to prove the liveness of PBFT. Let me start by defining more precisely what we mean by liveness in this context. So recall that we are implementing state machine replication. That means that processes submit commands for execution. The state machine replication protocol orders these commands, and then processes execute these commands in this order. So now the key liveness property you want to hold here is that any command submitted by a correct process is eventually executed by all correct processes. In particular, there is no censorship. So for example, the leader cannot selectively omit some commands that it doesn't like. To ensure this, in PBFT, processes monitor the leader's behavior, and they call advance if they suspect that the leader is faulty. And if nobody complains, and so nobody calls advance, everybody is happy, then the processes may stay in the same view potentially forever. Here is how this monitoring happens in more detail. Let's say we have a system of 4 processes. The leader is the process number 4, and let's say it's faulty. And process number 1 wants to submit a command C for execution. So then this process will, of course, forward this command to the leader. So with sending the command to the leader, it will also set a timer for the expected duration during which the protocol should process this command and finally execute it at process 1. For PBFT, this is 4 delta. If the timer expires before the command is executed at process 1, then the process will call advance and so complain about the leader because it's too slow. Now I'm setting the timer to 4 delta here. Before I told you that delta is unknown to the protocol. For the moment, let's just assume it's known, and later I'll explain how to deal with unknown deltas. Okay, so now using this mechanism, a process may complain if the leader is not executing its commands. But the problem is that one unhappy process is not enough to change the view, and so to change the leader, because we have this progress property of the synchronizer, and this property only guarantees a view switch if at least f+1 correct processes call advance. And so for this reason, when a process submits a command to the leader, it will actually also send it to all the other processes in the system, say processes 2 and 3 in this example. When these processes receive the command, they will also set the timers. And if the timers expire before the command is executed at these processes, they will also call advance and so complain about the leader. And so in this way, we can ensure that if the leader is faulty, the processes will notice it and try to change the view. Now, we're not done yet, though, because there is a flip side to this scheme. Let's assume now that the leader is actually correct. So that's process number 4. And process number 1, who is submitting the command, is faulty. So then what this process may do is it may send this command to all the processes in the system except for the leader. These processes will set timers for this command. And then these timers will, of course, expire because the leader is not submitting this command for execution, well, because it doesn't even know it exists. So then we may falsely suspect a correct leader as being faulty. So to deal with this, each process, when it receives a command forwarded by another process, it will also forward it to the leader. And in this way, we make sure that the leader can actually execute this command, and we don't falsely suspect correct leaders. Okay, so this is the overall scheme of the PBFT protocol. Now, let me say a few words about how we prove its liveness. It's the end of my talk, so I'm not going to go into a lot of detail here. I'm just going to give you a flavor for what kind of statements, intermediate statements, we have to establish to prove liveness of this protocol. And to recap, what we're proving is that any command submitted by correct process is eventually executed by all correct processes. The proof is kind of interesting because to ensure this property, both the state machine replication protocol, so the PBFT that I've shown you just now, and the state machine and the synchronizer, they both have to do their part. And the proof is essentially an interplay between the properties of these two sub-protocols. We think that the structure of this proof can be reused for proofs of other protocols because it establishes properties similar to those of failure detectors. The first such property is analogous to the completeness property of failure detectors. It says that if a correct process never executes some command it received, then eventually it will call advance. And so this is ensured by all these mechanism of timers that I've just shown you in PBFT. Now, commands are also distributed to all correct processes in PBFT. And so this means that if some command is not being executed, then all processes will complain. And by progress, that means they will switch a view. And so this gives you the ability to leave a view with a faulty leader. The next property is analogous to the eventual accuracy property of failure detectors. It says that eventually, in a view with a correct leader and high enough timeouts, no correct process will call advance. Here, all this mechanism with timeouts also plays a role, but the synchronizer also has to do its part. In particular, the proof of this property relies on the bounded entry property of the synchronizer. So recall that this bounded entry property is the property that ensures that all processes enter a given view. And that's important here because this means that all processes enter the view. And so if the leader is correct, then it can actually do the voting and reach a decision. And so then no process will complain and call advance. And now if we have such a view where the leader is correct, all processes are in this view and they keep executing all the commands they submit, then validity implies that the system will stay in this view forever. Because validity says that you can only enter a new view if some correct process called advance. So if nobody complained, then you will stay in this view. And so this is the overall proof structure. Now there is just one subtlety here, which is in eventual accuracy, I set high enough timeouts. And this means I have to set timeouts to something like 4 delta for PBFT. If the timeouts are set too low, then I may just complain spuriously too early. But I don't know delta, so I don't actually know how to set these timeouts. And unsurprisingly, to deal with this, each process will increase its timeouts when calling advance, so that these timeouts eventually go above the necessary values. What's more surprising here is that you need to be a bit careful about this in the proof. Let's say process 1, its timer expires and it calls advance. Then what may happen is that this may lead all other processes to switch to the next queue very quickly. For example, if faulty processes cooperate. And because these processes, their timers didn't expire and they didn't call advance, they will not actually increase their timeouts. And so one part of the proof is to actually prove the absence of pathological scenarios where some processes keep increasing timeouts because they're the first ones to call advance, and some processes never do increase timeouts. And so this is something we address in our proof. So this is a bird's eye overview of the proof. You can read the full pseudocode and the proof in our paper available on arXiv. There we also provide a detailed latency of analysis of the protocol, showing how quickly it reaches decisions. And there are also some other case studies, for example, a variant of the hot stuff protocol. And before I emphasize that our synchronizer fast sync runs in bounded space, so with a bit of work, you can actually make sure that PBFT, when used with this synchronizer, also runs in bounded space. And so the protocol is not susceptible to out-of-memory attacks. Okay, so to conclude, I've presented a framework for separating liveness and safety management in Byzantine state machine replication. And its distinguishing feature is that it implements state machine replication directly without going through consensus using the synchronizer that I talked to you about. Now, of course, because this is a thesis seminar, I should compare with Tenderbake, which is its new consensus engine that was presented here a while ago. Tenderbake uses consensus for state machine replication almost as a black box, but not quite. So I would say it's a gray box construction. And one of the key differences between our framework and the one used by Tenderbake is that we enable optimistically responsive protocols like PBFT or hot stuff. These are protocols that run at the speed of the network, so the protocol can proceed as soon as it gets enough messages, for example, a supermajority, without waiting conservatively for any timeouts. Whereas Tenderbake uses a simpler type of a synchronizer based only on timeouts, so it doesn't use anything like our wish messages, and because of this, it loses optimistic responsiveness. And so we hope that in the future, our results can be used for a next generation, better version of Tenderbake. And so that's the end of my presentation, and I'm happy to take questions.
Thank you, Alexey. Yeah, it would be great. I mean, there's always place for improving things. I'm just wondering about the trade-offs. Like right now, basically, we exploited the fact that Tezos relies on clocks, on NTP, basically. And so we don't exchange messages. I mean, anyhow, in Tezos, we don't have messages, that are operations and blocks. So the wishes should be some sort of operations. And to me, what's not clear if like in Tezos, we don't have any guarantees about the peer-to-peer. We can't, like a baker can't send the message to another baker. How problematic would be dealing with a peer-to-peer that doesn't give much guarantees in order to apply your results?
So we actually thought a bit about this. So if you assume that you have an overlay network, right? So one peer is transitively reachable from another one, right? Because if you have network pricing, then all bets are off. Then I think you can actually implement this still in bounded space. Using pretty much the same rules. So just every process, it will forward what it receives, for example, the wishes to all the other processes, and it will only need to maintain the highest wish from each process. Right? So this solves the problem with bounded space. So in general, you can always sort of say, if you have transitive connectivity, you can or just keep forwarding everything you receive, but then you have to buffer it. So here you can do the same tricks we played with forwarding, restricting to only forwarding what's necessary, and it will still run in bounded space. So I think that works now. If you don't have even transitive connectivity, then this is a completely different problem.
Yeah, I wanted also to. basically, you were also saying in the beginning, we're making the difference between permission and permissionless. So PBFT, like you say, you stay in the same view, so you have the same leader. So what would be the implications, like if you want to have take into account that you want to change the participants in consensus on a regular basis? What would be the implications? How would the synchronizer need to change?
Well, not necessarily. So first of all, so as I said, we sort of considered the construction from black box consensus suboptimal, and I just gave one illustration why that was reusing the leader, which is what PBFT does, right? So PBFT ideally it kind of converges into one view and then stays there forever. Now in practice, this will not be like this. So actually, in the extended version, we have a version of the protocol that periodically rotates the leaders.
The leader.
What you, I think, what is so it's not just about the leaders. If you take protocols that sort of have like hot stuff philosophy, where you think of every block essentially as a view, sometimes they call it like this, then a view here is something different. It's just more like agreeing on some other parameters, and these can be the timeout values, right? Because if you don't want to increase them with every view, right? So when people write theoretical papers, they say, oh, this can be just an increasing function of the view number, and then you'll hit what you need. Or the reconfiguring the membership of the system, right? So I think it's the synchronizer won't change. It's just when you need to do a heavy-handed change, you will have to call it once. But within a single view, for example, you can agree on a rotating schedule or among participants, right? So, this is like, so there are protocols like spinning, for example, that do this kind of thing, where for them view is, like, they have like views and epochs are kind of like our views. So these are like long-term things, but within them, the leaders keep rotating according to a given schedule. And then if something goes really wrong, then you really do a view switch where you start to sort out, well, what's the state of the system? Let's kick some people out or things like that. Yeah. So I think we did this just we took this decision just because this was the simplest example to demonstrate, but it's not restricted to that.
I see. Thank you. I see Sylvain. Sylvain has a question. So if you could say a word about the complexity number of messages of the protocol in the framework.
So the synchronizer is quadratic in terms of the number of messages. You can build a version of the synchronizer that, if you want, that reduces a bit the number of our messages at the expense of our sending kind of bigger messages, in the sense that if you gather, say, a quorum of wishes, you can just package it into a certificate and then send it to everybody. And this is something they can trust because it has enough signatures to just take it. Now, we think that that's okay in the sense that the word, if the question, so there's been a lot of like sales pitch stuff in the POTC community about the message complexity of our Byzantine Consensus and message complexity of view synchronization. Now actually there's a bit of a kind of a lies there, in the sense that people say, oh, hot stuff is linear, like for each decision you get a linear complexity, but that excludes the synchronizer, and our synchronizer is quadratic. There is another paper at DISC 2020 by Naur and Kedar, so this is the paper I cited in one of the slides, where they show an expected linear synchronizer. So it's I think it fits into our framework, so you can prove that they have like a different specification that's like more complicated, but I think you can prove that it satisfies our properties. But that's only expected linear, so not hard guarantees. And if you take the worst case, it may actually be, what we do may actually be optimal, we think. So and even if like just as a kind of an anecdote, if you look at the latest iteration of this Deem or aka Libra project from Facebook, okay, it's now dead, but there is the protocol is out there, and I think people are doing the same stuff in some startup. It's not actually hot stuff, it's PBFT, really. And the reason is that, I mean, it's like kind of not you need to look at it a bit closer to see the difference. Like PBFT rewritten into a hash chain with lots of optimizations, but it has like 2 phases instead of 3 like hot stuff. And essentially the reason why they did it is why bother with hot stuff if the message complexity is going to be bad because of the synchronizer? You're not going to get the linear message complexity. The promise of hot stuff is going to be, we're going to give you linear message complexity in exchange for 3 phases of voting instead of 2. And so they just went with, essentially, it's like PBFT. So I'm going to complete my rant about message complexity of Byzantine Consensus protocols. But lots of POTSI papers about it. There are still submissions coming in. Okay.
Yeah, this is was a crucial point in Tezos, because initially we wanted to get rid of the reliable broadcast assumption they make in Tendermint, and for that we wanted to include the pre-endorsements as a certificate, as a proof, the way we have to do that is to include them in the blocks, and by doing so you have bigger blocks, and so that was a no-go. But speaking of bigger blocks, basically, I mean, with you say you would have optimistic responsiveness, but on the other hand, I mean, it's not just like being able to react as fast as the network, but it's also like you have to validate the blocks in blockchain, so that also takes time. So in hot stuff, if doesn't matter that they have optimistic responsiveness if it takes a lot of time to validate the blocks, so that kind of takes time as well. So I was wondering also, like, if you have concrete examples of optimistic responsiveness in practice, like what would really, I mean, also if it's in synchrony, if things go well, Tenderbake goes fast. I mean, you have it's up to the duration of the round, and then.
Okay.
So I was wondering,
Okay, so I gave on this last slide, I gave a diplomatic answer in the sense that it was like a mathematical criterion, kind of like that you say, you don't satisfy, we satisfied. Now, a bit like, but the differences go a bit beyond that in the sense that, so apart from optimistic responsiveness, Tenderbake is kind of complicated with this recomputing the timeline and things like that, right? So you're like, you're in some view, and then suddenly you realize, I got some certificate saying. So essentially, to figure out where you are in which view you need to know what the minimal, in some according to notion of a minimal certificate decided in the previous view, because that in the previous instance, because that kind of tells you where the timeline of the previous instance finished. And now, if you suddenly find out about there's some other certificate, then you need to recompute this whole timeline and do something else. And this just
it's computing numbers. It's simple. I mean, it's fast. It's faster than sending messages.
On diplomatic answers, it sounds a bit inelegant, right? In the sense, right? So that's like, okay, but then you can, we can debate how, important that is. And the other thing with, so with optimistic responsiveness, so the issues also so one issues are how, because the Tendermint, you can sort of make it work okay if everything goes all right in the first view. So the problem is, how long are you going to wait in the next view and the next view, right? If you need to fail over across several faulty leaders. And when we did latency analysis, we show that because we only increased time. So with this mechanism of wishes, we can only increase timeouts if things really don't go well, if we suspect that things don't go well. So if you just sorry, I'm getting a bit sorry, I've confused you a bit. So essentially, like, I think what our approach allows you is to minimize also the waits during bad periods. Right, so for example, we have latency bounds like, you'll recover in at most one maximal timeout value and things like that, and that's because we won't rely on timeouts to kind of detect faulty behavior, but not to achieve view synchronization per se. We have wish messages for this, whereas Tenderbake will, if you start growing, if you start getting views, you start switching through views, and you will only be able to do view synchronization by growing these timeouts and sort of for no particular reason, because there are no faults. Sorry, I guess I gave a confusing answer.
But you also increase the timeouts, right?
But only so I guess the difference is when we only increase timeouts if you are so maybe so we only increase timeouts if there is if we know something is not going well. Whereas in tender bake, right, if you switch to another view for whatever reasons, right, you need to if you need to resynchronize, the only way to do this is to essentially let me try to answer this we will never have to increase timeouts beyond the maximal network delay that you could have, right? So imagine you have like a conservative value for the maximal network delay. We only increase timeout to approximate the network delay. Whereas with tender bake, if you take a synchronous period, right? So like last, and then you have synchronous period. During the asynchronous period, you may need to increase timeouts. During the synchronous period, you may need to increase timeouts a lot just to get the overlap, right? Because that's the only mechanism you have to get everybody into the same view.
If I'm in the synchronous period?
Yeah, so let's say you have an asynchronous period, right, first, and then, everybody's out of sync, right? Then there is the synchronous period. The only mechanism you have to bring people into the same view is to keep increasing timeouts.
Yep.
And you don't know for as long as necessary to get the overlap, right? Whereas we will just send wishes and they will get through during the synchronous period. And the timeouts will only increase them to approximate the message delay and not beyond that, right? So you have some conservative estimate of message delay. So there are models like this. Then that's the top to which you will need to increase the timeouts for the protocol to work.
Yeah, thank you. So yeah, speaking of sending wish message, there's also the problem of spamming, right? If you have crazy participants sending lots of wishes, so.
But you only need to maintain the latest
the
one,
highest,
right? So memory is not an issue. CPU is yes, but it's sort of like a DDoS. I mean, you could DDoS them in all kinds of. Yeah, I think whatever solutions you have for DDoSing, whatever, with block proposals or something, you should use them here. Right?
I see Eugen has also a question. So he says, are wish messages necessary in the normal path when the decisions are taken in the first view? Can they be piggybacked on the consensus messages to reduce the amount of exchanged messages?
So so this kind of goes back to the answer I gave about what is a view and whether you need to maintain the same leader during the view. So in general, you can have, or a view can be some very long-lasting thing where you can still different leaders, when you can keep committing new instances, and different leaders may be responsible for different instances, and the view just governs the how things are, the schedule or parameters or whatever. And during this time period, you never call the synchronizer. Right? So if everything goes all right, you will never complain. So there are no wish messages. So the synchronizer, you will only call it when something is not right, like you're not getting the committing, some instance getting committed quickly enough, and then you will actually call the synchronizer. If you want to use consensus kind of as a black box or closer to a black box, or this is like for example, for this consensus for synchronizers we gave in our previous paper, then what you could do there is you could kind of piggyback wish zero messages for one instance on the decisions of the previous instance. You could potentially do that. That's another alternative.
I see. Thank you. Yeah, it's a pity you didn't mention the liveness issues that you found. It's
I was being diplomatic because this was gonna be on YouTube, but I can entertain the audience. So we had a complicated. So this second paper that we wrote, we had a complicated story with the first submission got rejected, and in particular, people were saying, the reviewers were saying things like, we don't think there are any issues with the current proofs of PBFT. And so I guess then this was a bit of a strange comment, because in PBFT, if you look at the thesis or the paper, then there is nothing there about liveness. In the journal paper, there's like half a page saying, just justifying kind of why the rules are like this, but it's not a proof. And we kind of asked around back then, and the only thing people could point us to was this book. So there's this book by sort of Reliable and Secure Distributed Systems by Christian Cash and Luis Rodriguez and Rashid Garawi. So it's actually used for teaching at quite a few universities. And so the book was kind of interesting. So because they tried to we have a proof of a single shot PBFT of safety and liveness, was like a simplified version, and it was also done using like a modular construction, where the building block was something vaguely similar to synchronizers, but not quite. It's more reminiscent of a failure detector. And so we stared at that, and then we found that the algorithm is actually broken. And the funny thing was that the algorithm per se, you can easily, that's in the book, you can easily fix it, but this will not fix the intermediate abstractions, right? So in the sense that because they came up with the wrong intermediate abstractions, they came up with the algorithm was eventually got broken. And essentially the reason is that because they were trying to be too much like failure detectors. And so failure detectors are a controversial primitive in the Byzantine context, because usually the failure detectors are these things that say, I think this guy is faulty, and they have a guarantee that eventually you'll actually suspect people in a correct way, that you will only suspect faulty people. And in Byzantine context, the notion of failure is protocol specific. So it's very hard to come up with an abstraction that would say, you're faulty. And so these slides I showed at the end about our proof essentially is what we do is our synchronizer is a much more sort of a primitive abstraction that does some bare bones resynchronization stuff. And then if you add some SMR mechanisms, like all these timers that know how the protocol is supposed to work, then out of that you can prove that you guarantee properties something like similar to failure detectors. But for that you need both synchronizer and the state machine replication protocol to do some work and to be aware of what the protocol actually is. So that's the story.
So given how tough these problems are, for when do we expect mechanical proof or something of
mechanic proofs? There's nothing wrong. I think you can take our proofs and code them up into coq, or then spilling some amount of blood, you can mechanize them. So we did quite rigorous proofs. I think it's more interesting to look at the more like SMT-based verification of these things. I think for liveness, it's kind of an open problem in the sense that for safety, there've been a lot of, you can use Daphne or things like that, and it's pretty easy to encode the distributed systems. This system specify a bunch of invariants and then do a machine checked proof. But for liveness, where you have to reason about these like approximations of timeouts, and you can have a model with the notion of time and timeouts, there hasn't really been that much work. I mean,
the work of Giuliano Rosa.
So Giuliano also they did something in Ivy that also sort of requires encoding the system in a particular way. So this is a bit of a I think we should solve some problems about how you do in general these kinds of proofs for liveness, and then we can you can code up our proofs.
Yeah, thank you very much, Alexey, for all your work. It's great what you're doing. If there are no more questions, I thank you again and thank the audience, and hope to see all of you next time. Bye.
Thank you very much. Thanks for inviting me.